Welcome back to Real Learning Center. We have started our course on laws of motion. So we have completed the first video. This is part 2. So part 2 is Newton's first law. So let us see what was there in our first video. Our first video was what was the cause of what causes motion. We studied Galileo and we studied Aristotle and we understood the concept of inertia. Now we are going to basically look into Newton's first law and see how Newton actually continued from where Galileo left. So what we saw in the first one was an object continues to move in the absence of any external force. So the object may be needing force to start motion or stop motion and all that, but it will continue to move forever in the absence of any external force. And Newton starts where Galileo ends his journey. So with the concept of inertia, Newton starts. So who's this Newton? What did he do? So that we will just get a glimpse of that before we move on to understanding his first law. So Sir Isaac Newton, one of the greatest physicists, scientists ever produced by us. So he is actually kind of worked in many different areas. He came a little later than Galileo. So he actually worked mainly on laws of motion, and you know about law of gravitation, how the gravitation works. So he worked on that. He even worked on things like laws of cooling. Yeah. If you keep some, let's say milk or coffee on the table, how long it takes to cool down. So he worked out laws on that. Okay. So he invented a new area of mathematics called as calculus, and he worked on corpuscular theory of light. He worked on light. He created a telescope to look at the planets, and he also said that white light has many colors, though it looks white. So he kind of worked on many different areas, and both theoretically, practically, and mathematically, many areas in which he contributed. So that is the great guy Newton. In fact, even Einstein, we consider as the greatest 21st century scientist actually. 20th century scientist kept his Newton's photo in his office. So he is such a great scientist. So now let us look at cosmology is another area he worked on. It is one of the he contributed a lot in the area of cosmology. So what is his law of inertia? So this is called Newton's first law, and it's also called as law of inertia. So let me first make this statement in Newton's language. He says that everybody preserves its state of rest or of uniform motion unless it is compelled to change that state by an impressed external force. So that is his statement, Newton's statement. So generally, when you work on laws, they look like this. They are not at first understandable, but when you understand it, they have very deep meaning. Okay. So if you want to understand it in very simple English, I would put it this way. If something is at rest, it will continue to remain at rest. If something is moving with constant velocity, it will continue to move with constant velocity. Unless, of course, some external force acts on it. That is all. He says that. He just clarified the concept of inertia. He said that it will continue to remain at rest or in uniform motion. Uniform motion means constant velocity. So we tend to use the word constant velocity instead of constant speed, because velocity has both its value, that is magnitude, and direction. Even when you are going at constant speed, if you change the direction, you are actually changing the velocity. So that's why we use the word velocity. Okay, constant velocity, unless an external force acts on it. If an external force acts on it, then it will change its velocity. That is all. So this is basically what I call as lazy law. So things are generally in the body are lazy in this universe. They remain at rest or in uniform velocity unless some force comes and changes it. This is called lazy law. Okay. So everything is in principle or by nature lazy. That is Newton's first. Inertia means for inert. Inert is laziness. So inertia is about laziness. Okay. So now, why should we believe in this law? Why do we accept this? So this is not some day-to-day experience for us. Now, our experience has been that if something is at rest, it will be at rest. And if I keep something on the table, and tomorrow if it is not there, you know, somebody else has moved it. It is not gone on its own to some other place. So we are very firm believers of the first part. So if something is at rest, it will remain at rest. But we are not such a great believers of the second part. And the day you start believing in the second part, you start understanding physics, because that is the most fundamental concept of physics. So let's now see how to actually get some clues about that from the world around us. Around us, whatever world we watch, we see clues of this. So we will see now what are those clues. Okay. So look at the first one. So just keep watching this. Okay, there is a truck and a car mounted on it, and they forgot to tie it up. When the truck moved, car remained in the same state of rest. Truck moved on, car remained in the same state of rest. Okay, so you can see here the people sitting in the car, and when the car actually went ahead with a lot of acceleration, people actually fell down. So they remained in the state of rest, and the car moved. Car moved by an acceleration, a force acting on it. No force acted on the people, so they fell down. So same is the case with the car. So these two things will clearly tell us that things tend to remain at rest unless some force acts on it. Okay, they tend to remain. When force acts, it will go. Yes, that is the tendency of the body. Now, let's also look at the other one. Look at this car which comes from the left with a guy on it, and when it crashes, what happens? The car crashed and stopped because the force stopped the car, the force of the crash, the obstacle. But the guy who was sitting inside, he was not wearing the seat belt, so he was thrown, and he continued his motion. So he did not stop. So now you understand maybe why we wear seat belts. Okay, so we wear seat belts simply because Newton's law, first law, is correct. Things that are in motion tends to stay in motion. So they will keep on going in motion unless you stop it somehow through some other external force. So these are some of the hints that we get that Newton's first law may be right. But what is important is that this tendency of trying to be there in where being at rest or in uniform motion, that tendency is actually called as inertia. Okay. That tendency, we named it as inertia. That is the first law. Now, if you see, the real evidence comes from the space travel. So now you watch this carefully. Okay, then it starts here again. So there were two spacecraft launched in 1977, Voyager 1 and 2. Okay. They were actually launched from Earth, and those spacecrafts finally, now after about 35-40 years, they have actually left the solar system and gone away. Okay. And they are now venturing into the interstellar space between after our planetary system, solar system. So who is what is pushing them? What force? What kind of an engine does it have? Liquid hydrogen. What does it use? So does it use gas? So none of them. Okay, it uses Newton's first law. You know what it does? So when it is launched from the Earth, in the beginning we gave it a lot of force, and then we actually derived some force through gravitation around another planet, and then afterwards, once it is going at a very high speed, it kept on going without any force acting on it. So, and it will keep on going, and we are hoping that it will one day reach some other star. Okay, so that is the power of Newton's first law. Okay, we know that it keeps on moving. Now today we have a very concrete evidence that things will keep on moving if you still don't have any force acting on it. Okay. That space travel has told us that. So now today it's actually moving at a speed of around 62,136 kilometers per hour. This is the speed with which it is moving, and it has gone beyond solar system. Both of them, they both have gone beyond solar system. Voyager 1 and 2, and it is not consuming any fuel. There is no force acting on it. It is going in a uniform velocity, escaping from our sun, away from us. Okay, no fuel for propulsion. So force is not needed to keep a body in uniform motion. So this has to basically get into our head to basically learn physics well. Okay, so this is the fundamental concept in physics. So let's see some examples of that we day to day use without even actually thinking about it. Okay, I don't know if you have used hammer anytime. Okay, there is this wooden thing, handle, and on that there is a hammer head. You can see as it is shown there. So let's say if the hammer head is slightly loose and you want to tighten it, any experienced guy will do it like this. He hits it down like this, and when he does so, the hammer head gets tightened. Why does it happen? Because when he moves it like this, his handle and the hammer head, both of them are moving. And when he hits it on the table, suddenly the hammer handle stops moving. But our hammer head doesn't know that. There is no force acting on that. The hammer head will keep on moving down. So it is like pushing the hammer head down onto the handle, and it gets tightened. So we use here actually Newton's first law to tighten the hammer head on the handle. Not just there, I will show you another interesting place where we can understand this inertia. Okay, so let's look at this interesting experiment. So what we are doing here is simply tossing a coin. Okay. You can very clearly see that coin goes up and comes back onto the finger right away. Now, suppose if I do this experiment in a moving train. I am standing in a moving train, I toss it and it will come back. So the question basically is, will it come back to my own finger, or will it come back at some other point, at the front or the back, depending on the direction the train is moving? So let's see. Okay, so let's get into a train. Okay, so we are inside a train. Okay. Now train is standing and you are still doing this. Now let us move the train. Okay, and along with the tossing continuing, let's move the train. So when the train is moving, you can very clearly see that the coin is going up and coming down onto the same finger. Nothing is happening. It's not going anywhere. It's just going up and coming down. In what way this is telling us about the inertia? So I am climbing that. The train is, you think that it is going up and coming down. But you know, it is also going along with the train. Because after a second of throwing, the person has actually moved. And the coin has to come behind here. But it is not happening. It is also falling on the finger again. Which means that it is also moving. How is it moving? Who is pushing it? Nobody is pushing it. It is in the air. If I am holding in my hand, I am pushing it. If it is in the air, who is pushing it? You can do it even in vacuum. If you think that air is pushing it, even in vacuum, it will keep on moving. So, the coin is actually not only coming back here when you are tossing it, it is also moving. Because once the train is moving, when it is on your finger, it started moving. And when it is up here, there is no force acting on it, but it kept on moving. Do you want to see this in action? For that, actually, you have to remove all the other things and just watch the coin itself. I'll show you just the coin. I'll make other things disappear. Okay. Let's look at the coin itself. So now you have this coin and it is going up and down, you can see. Okay. Now I will actually put the train here. Okay, it's going up and down. Okay. Now I will actually remove. I will just hide the train and the hands and show only the coin. So I'll just make it disappear. for you. You can clearly watch that the coin is going up and once you check it is there. The coin is there, hands are there, and the train is there. I have made it disappear for you to see. Just watch coin without the other things in picture. Okay. So what will happen? So I'll show you what will happen. Okay, just keep watching this. I'll just show you what will happen. I'll now make it move and just trace the path of the coin. Did you watch? You want to watch again? So let's see. Watch again. Okay, I'll show you. So did you see the coin moving like this? Coin actually taken a path something like this. I don't think we ever threw the coin like that. So coin is not only going up and down, coin is going sideways. Why is coin going sideways? That is because it kept on moving along with the train and it has its inertia. Coin has been traveling along with the train and hence has its velocity. Okay. And hence, even while going up and down, it is traveling from left to right. It has kept its motion, uniform motion from left to right while doing up and down. And that is what we call inertia. So coin was exhibiting inertia for it. So this is another evidence. If you carefully watch, you can see of Newton's first law. So we have come to basically a basic understanding of Newton. There is nothing very difficult to understand. It is but hard to accept. So the moment you accept Newton's first law wholeheartedly and you understand this, then we can go forward to other parts of the Newton's laws. So we have completed what causes motion, and we found out what Galileo did, what Aristotle did, and we found out how Newton actually postulated his laws and how we can see them, the Newton's first law acting everywhere around us. So that's where we have reached now, and we are going to have 4 more videos. Please keep looking for, go and look at the next video and get an idea of what Newton did after this. After the first law, what came. So let's talk about the second law in the next video. Thank you. All the best.